Covalent bonding. Right, so all of our bonding, all of our atoms and stuff have this idea of the octet rule, right? So metals like to lose their outer shell electrons readily, form the metallic bonding model, right? Ionic compounds have a metal and a non-metal, so we donate or receive an electron in order to be satisfied, right? This octet, oct meaning 8 electrons in the outer shell. So remember, we cannot have more than 8 electrons in our outer shell, right? So this octet rule goes on for all of our types of bonding, particularly covalent. And it especially applies to these non-metal compounds, non-metal atoms, carbon, nitrogen, oxygen, and halogens, but also to other metals such as sodium, magnesium, aluminium, group 1, 2, 13. So we've got quite a bit to cover in covalent bonding. So obviously we're not going to get through all of this today. We might get through a bit of definitions and starting to represent them. And then in a later class, we'll look at molecular shape and then compare the 3 bonding models together. So defining what a covalent bond is, right? Which elements are most likely to participate in covalent bonding? Well, that's going to be between non-metals, right? So in metallic bonding is within metals, right? Ionic bonding is typically between a metal and a non-metal. I say that because we know we've got our polyatomic ions that are made up of non-metallic atoms. So something like ammonium nitrate doesn't have any metal in it at all, right? So it's important to understand that distinction. But generally, metal and non-metal is ionic. So covalent is between non-metal and another non-metal together. Make sense? Good. If we want to describe the behavior of electrons in metallic bonding, we have that cloud of electrons, or that sea of electrons, right, that float around the metal cations and holds the metal together. In ionic bonding, we've got that transfer of electrons, the donation and acceptance. In covalent bonds, it's the sharing of electrons, right? And this relates to when we don't have large differences in electronegativity, so one isn't stronger than the other in order to strip the electron away. So we share instead. So for example, if I have a red pen, you have a blue pen, but we put both pens on the table, we both have access to both coloured pens, right, at any one time. So we share the electrons in order for the atoms to achieve their full outer shell, or have access to 8 electrons in total. Any questions?
What was the type of bonding that goes between the metals again?
Metal and metal, metallic. Yeah? Question?
When they're sharing it, like this is between like elements, right?
Yep.
Yeah. So they can just both like access them whenever they.
Correct. Yeah. Yep. Question? Yep.
Oh, yeah. Why is it the same? Like, can it be the same type of bond?
Same type of bond.
Like electric and
Well, you're not going to have both types of bonding in a substance. Yeah?
Yeah.
But in metallic bonding, it's the pure metal we're talking about. Right?
Oh, yeah. So it's just the difference is what they're bonding.
Yeah, exactly. Other questions? Define the term molecule. A molecule is a discrete unit, right? Generally made up of 2 or more atoms that are covalently bonded together. What do I mean by the word discrete? What does that mean? That's the opposite of continuous. So in metallic and ionic bonding, they're continuous. They're these 3D lattice, regular arrangements of alternating patterns, right? Covalent bonds, it's a discrete, it's one. We have a discrete number of students in this classroom. There are 23 students, not 23 and a half, right? Not 23.27. can't have 0.27 of a student. Yeah? Whole numbers, I can count them. That's what the word discrete means. So in maths, discrete variable is one in which can be counted. Right? Continuous variable generally is a variable in which can be measured. Right? And the limitation is the tool in which you are measuring with. So a chemical bond formed by the sharing of electrons is called covalent. And as stated before, it's between non-metal atoms. Any questions there? I'll pause and give you a moment. Okay, so how do we represent them? Identifying how many electrons in groups 15, 16 and 17 and hydrogen are likely to share and the number of covalence bonds that these elements will form. Right, so if we go back to, for a moment, I'll blow this up so to see me and the board. If we blow up, go back, right back to one of our first lessons, and we started looking at the Bohr models of an atom. If we look at something like the Bohr model of carbon, looked something like it had 2 in the first shell, and then it had 4. And remember I said we go up to 4 before we start pairing them up. That make sense? The number of unpaired electrons are the number of bonds that it's available to form. So carbon has 4 unpaired electrons, which means how many bonds can it form? 4. If we look at, say, nitrogen, that's the next element along. 1, 2, 3, 4, 5. How many unpaired electrons does nitrogen have? 3. How many bonds does it want to form? 3. Awesome. Then we go to oxygen. Oxygen. 1, 2, 1, 2, 3, 4, 5, 6. How many unpaired electrons? 2. How many bonds does it want to form?
2.
Awesome. And then we go to fluorine. And we start to see this emergent pattern. 2, 3, 4, 5, 6, 7. 1 electron. 1 bond can form. Neon. 1, 2, 1, 2, 3, 4. Pair up. How many unpaired electrons?
0.
None. How many bonds is it going to form? 0. Exactly right. So there we go. Switch back to here. So the number of unpaired electrons are the number of bonds that it wants or is available to form. Because it wants 4 to complete its octet. This wants 3 more to complete its octet and so on. Notice the inner or the full shells are not involved in the bonding process. It's only ever the valent shell in which bonding occurs. So here we go. That's group 15. That's group 16, 17, 18. And then hydrogen. What's the electron configuration of a hydrogen atom?
Just 2.
Just 1.
1. How many bonds does it want? 1. Because how many can we fit in the first shell? 2. Excellent. So group 1 wants to form 1 bond, as well as group 17 wants to form 1. Hydrogen's special in that it's a half-filled shell. So it acts a bit like a carbon, right? In that it's half-filled. It's 1 electron, but it's a half-filled shell. There are 2 main ways in which we're going to represent elements. One is called electron dot diagrams. The other is called valence structures or structural diagrams. So electron dot or Lewis structures as we may call them, and structural diagrams or structural formula. Electron dot diagrams uses dots to represent electrons. Makes sense, yeah? But we're only looking at the valence shell, right? Can we go back? Oops, let's go back. Okay, let's continue. So 2 things that electrons like. We want 8 electrons in the outer shell, and they want to be in pairs, right? So we've talked about that before. Steps to drawing electron dot diagrams. We want to fill the valence electrons up until we get 4. right? And then we start to pair up, but we want to pair up and continue in the same direction, right? So notice how in oxygen I've got a pair here and a pair here rather than a pair up and down. Make sense? Yeah? This is important because it will help reduce the number of mistakes when we come to identifying the shape of a molecule. So we split this into unpaired and, we've got a non-bonding pair, right? And these will form what's called bonding pairs. Okay, so here's the first 36 elements, ignoring the transition metals. And I've broken this up into little quadrants, if we want to think about it that way. In this orange quadrant on the left-hand side, all of these elements form metallic or ionic bonds. Yeah? They will lose their outer shell electrons very readily. They have very low ionization energies. Those electrons very easily lost, and typically will form bonds with one of these atoms over here. These other atoms in between, right, in the middle, will all form covalent structures. Notice that beryllium and boron, despite them being in group 2 and group 3, they're a bit special. They're special exceptions to the octet rule. And we'll talk about them, but it's more of an extension. So beryllium and boron, I'll talk about those. And obviously, our noble gases, they're inert. They're called inert because they're unreactive. They have that full valence shell. We can see these electron dot diagrams as to how they appear. So making sure that we are drawing them in the appropriate fashion. Okay, so let's look at the simplest of examples is hydrogen gas. Hydrogen gas. Each hydrogen atom has one electron. Each hydrogen atom wants to have 2 electrons. So they're both going to share one electron and form a single covalent bond. One bond, 2 electrons. Yeah? For every covalent bond will contain 2 electrons. Make sense? Yeah? Now, the thing I want to point out is that in electron dot diagrams, we don't include the circles. The only reason I've represented the circles here is to illustrate that both atoms have access to both of the 2 electrons. In reality, let's blow up this again. In reality, right, if I have a hydrogen atom, the electrons aren't static, right? So I've got a hydrogen atom with 1 electron, another hydrogen atom with another electron. If I was to take 1 billion photographs, right, of a hydrogen molecule, we would find at one singular point in time an electron will be there and an electron will be there. If I keep taking more and more photographs, what we start to find is that the majority of the time, the electrons will occupy in that space there, right? And so we can think about electrons as being a density of where approximately they're going to occur. So we simplify that down to as displayed in the presentation here. 2 electrons shared between the 2 atoms. Okay? All right.
How do they bond? Are they
Just share. Yeah? This is a representation. How do they bond? It's an attractive force. Yeah? So all bonding, right? All bonding is electrostatic. In metallic bonding, it's between the metal cation and the sea of delocalized electrons. In ionic bonding, it's the force of attraction between opposed charges. In covalent bond, it's between the shared electrons and the positively charged nucleus. Second example, fluorine. 7 electrons in the outer shell, wants 1. What do we notice? I'm going to move the